Okay, welcome to week 3. So last time we introduced the quantum master equation, which you can see on the right-hand panel. So this is an equation for the time-dependent probability of being in state A, and it's in terms of itself, and then also a quantity P AB, which is the probability of making a transition from a state A to a state B, the probability of unit time. The rate at which the transition actually occurs, of course, depends on being in state A in the first place. So you have to multiply by the probability of being in state A. And so you end up with the rate of going from A to B is omega A times PAB. And in those terms, in terms of the rates, the master equation is written down as the equation I just starred over on the right-hand panel. What we're interested in is what happens at long times, and it's a matter of experience that as you go to long times, systems go to thermal equilibrium. Unless they are being driven, it's an isolated system that we're interested in here. So, excuse me, the condition for stationarity is that the sum over states B of RBA minus RAB is equal to 0. RBA we think of as the forward rate, RAB as the backward rate. The rate of going from A to B, and the rate from going from B to A is the backward rate. So there's two types of solutions to this stationary equation. The first solution is obviously that if RBA minus RAB is equal to 0 for every pair of states A and B, that's what we call thermal equilibrium. So every single forward transition is balanced by the corresponding backward reaction. And so that's called detailed balance. And in the lecture, I derived from that the principle of equal a priori probabilities. There's a second way that we can get stationarity, which is that the rates themselves do not balance, the forward and the backward rates do not balance, but if I sum over all states, then they do balance. And that is what you would get if you had a non-equilibrium steady state, which is not what we are going to deal with in this course. So then what we did is I showed you that we can use this principle of detailed balance, the idea that the rates and the forward and backward rate balance out, cancel out in thermal equilibrium. We can actually use that to compute something. So as an example, as a very ambitious example, if somebody knocks on the door, you'll have to let them in, okay? As a very ambitious example, we decided to do a very interesting problem, a real quantum problem, ideal fermions, subject to a vanishingly small interaction so that we actually can apply statistical mechanics. And the idea then was that we're going to simply look at what happens to the scattering process shown on the right-hand panel, where two fermions in states 1 and 2 collide and end up producing states 3 and 4. And what we're going to try to do is see what is the single particle distribution function. In other words, if I have a set of fermions, I can measure the fraction of fermions in any given quantum state, and I can ask what is the probability distribution that I will find fermions in these individual single particle quantum states, and we're going to calculate that using the principle of detailed balance. So what we did was I first of all wrote down what is the forward and backward rates. And the forward rates we got from using time-dependent perturbation theory, which is how you derive Fermi's golden rule. And we just quoted Fermi's golden rule. So the rate is proportional to a matrix element squared, a matrix element between the initial and final states, many-body states with the interaction Hamiltonian, which I call H1. And then there were the phase space factors, which I called, which are these ones over here. F1, F2, 1 minus F3, 1 minus F4. And the logic behind those is that if you think about the occupation numbers of any given state, for fermions, it can either be 0 or 1. So if we're going to make this transition, we first of all need to have the initial states be occupied, and we also need to have that the final states are empty. Otherwise, you can't make a transition into them by the Pauli exclusion principle. So that means that we would expect the phase space factors to be F1, F2 times 1 minus F3, 1 minus F4. And those functions are actually not really 0 or 1. Okay, they are really expectation values of the occupation numbers, and so they will not exactly be 0 or 1. And in fact, what we're going to find is that these things are actually the Fermi-Dirac distribution, which I derived at the end of last lecture, which I'll get to in just 2 minutes. So in the discussion session this afternoon, I will go through the real derivation of these phase space factors using quantum mechanics and annihilation and creation operators. So what I did in class was I tricked you. I said these occupation numbers are 0 or 1. So if the states are going to be empty, then that means that we have to have F1, F2. If the states are going to be initially empty, we have to have 1 minus F3, 1 minus F4. If they're going to be occupied, we have to have F1, F2. It's not quite correct because these functions F1, F2 as functions of energy are not exactly 0 or 1. They actually have a shape, which those of you who've done this before know is the Fermi-Dirac distribution, which has a sort of hyperbolic tangent profile between 0 and 1. Now, what was the strategy for solving this problem precisely? So the strategy was we're going to make the forward and backward rates equal. So we did that. The matrix elements are Hermitian. So the matrix elements just cancel out on both sides of the equation. And we ended up with a functional equation for the quantity phi of E. And that quantity phi of E is the one that I've defined over here. It's f of E over 1 minus f of E. And that's how we got by equating the forward and backward rates. And then what we said was, well, the actual functional equation turns out to be the one I've written below that. Log of phi of E1 plus log of phi of E2 is log of phi of E3 plus log phi of E4. And we're trying to find what is the function phi of E that satisfies this. And it's not just that one equation. We also have the conservation of energy. So we know that E1 plus E2, the energy in the initial state and the energy in the final state are equal. So E1 plus E2 is equal to E3 plus E4. And something got missed out here. So then we can actually solve this by inspection. Because when we look at this, we can see the only way that the conservation of energy could be consistent with the equation we got from the principle of detailed balance is if log of phi of E is a linear function. But if it's a nonlinear function, then it won't possibly satisfy that equation. But if it is just linear, a constant plus a linear piece, then it will satisfy both the conservation of energy and the functional equation we got from the principle of detailed balance. So then, knowing that log of phi of E is alpha plus beta E is the unique, the most general solution of this functional equation, then we can rearrange it using our definition of phi. And at the end of last lecture, what we ended up with was the equation shown down here on the right, where we see that F has the form 1 over 1 plus E to a constant plus beta times the energy. And just to remind you, what is F of I? F of I is the average occupation number of the single particle quantum state I in thermal equilibrium. Okay, and EI is the energy associated with that quantum state. Okay, so that's what the Fermi-Dirac distribution is. All right, so now what I'm going to do in today's lecture is I'm going to determine what alpha and beta are, and I'm going to do that by requiring that our Fermi-Dirac distribution maps in to what we already know happens for the quantum system in the classical limit. And how do we know that? Well, remember the previous lecture, we derived the Sackur-Tetrode formula. We did all that stuff using delta functions and funky math. And in the end, we derived this formula for the entropy of the ideal quantum gas. And we discovered this formula, which had Planck's constant in it, and it was definitely something interesting. And the puzzle was that that equation gave us the equation of state of a classical gas. And we solved that paradox by saying, oh yes, what we actually derived was the classical limit of a quantum gas, because we didn't take into account the symmetry of wave functions. We didn't take into account the fact that if you have ideal quantum particles, their wave functions either have to be symmetric or anti-symmetric, at least in 3 dimensions. So in this calculation that we did here with the principle of detailed balance, we did take that into account. That condition, that the anti-symmetry of wave functions, is exactly what gives rise to the Pauli exclusion principle for fermions. So we actually have now derived a bona fide quantum expression, and now we're going to require that in the quantum limit, it ends up being equivalent to the Sackur-Tetrad formula, and we're going to see that that is indeed the case. Okay, Andrew, you had a quick question before I continue?
Well, I just thought I'll save it for discussion.
Okay. If you have questions that do not need to be asked in the class, then just save them for discussion later. But if they are needed for clarification or to correct a mistake that would be of interest to all the other students, please don't hesitate to ask them. Okay, so now let's, that's what we're going to do. That's in section 2.3.4 of my printed notes. Then we're going to look at systems in thermal contact. Now, up to now, all we've talked about is a system in isolation. One box of stuff just sitting there. Now we're going to talk about what happens when we put systems in thermal contact. We're going to derive the second law of thermodynamics, and either today or on Wednesday, we will derive the Boltzmann distribution. Okay, so finally, before I get going with the class, I want to remind everybody that on Thursday we have the Dashen lecture, which is a colloquium. And it's of special interest to all of you in this class because it is given by Professor Juan Maldaceno, who's very, very well known in contributions to string theory and things like this. One of the things, what he's going to be talking about is the entropy of black holes. And if you remember at the beginning of this class, when I told you about reasons to study statistical mechanics and why it is not just something for biophysicists or condensed matter physicists, on the homepage of the class, I gave you some examples of the way that statistical mechanics is connected to general relativity, quantum gravity, and black holes. You're going to hear that at the Dashen lecture on Thursday. So make a point to go to the Dashen lecture. If there is an event where students can sign up to go to lunch with the speaker, I encourage all of you to do that. It will be enormously interesting, and it's a great opportunity. Okay, so now let's roll up our sleeves and get chalk dust all over ourselves and do a calculation. Okay, so Jake, you have a question?
Yeah, sorry, quick clarification. The average occupation number, is that saying like in a state of 10 to the 23 atoms, this many are of this energy?
Yes.
Okay.
Not of this energy. In this state.
Okay.
That's something different.
Yes. Where does the total number come in?
I'm about to explain that. Okay, so we've got two unknown quantities in our formula, and we need two equations to determine them. So the first equation is that we are dealing with an isolated system. So two things are true. One is that the particles are all conserved. We're not doing anything relativistic here. So the total number of particles must be equal to the sum over k of fk. In other words, if I sum over all quantum states, look at the occupation of every single quantum state, find how many particles are in each quantum state, add them all up, I've got to get the total number of particles in the system. So that's the first conservation law. The second one is that this is an isolated system. So the energy of the system must be conserved. So if I know I've got a particle in a quantum state k, say as specified by its momentum, then I know what is the energy of that state, because the energy is just p squared over 2m. These are ideal particles, so the energy of a state of a particle with momentum p is just p squared over 2m. So I know the energy of those particles. So if I want to get the total energy of this system, I sum over all the quantum states, the occupation of those states, how many particles are in that state, times the energy of that state, and that will give me the total energy. So these are the two constraints that we are going to use to calculate the unknown constants alpha and beta. And we're going to do this with a clever trick as usual. What we're going to do in both cases is I'm going to say, what have I told you so far? I want to try to use only things I've told you so far. What I've told you so far is we already know what is the classical behavior of our isolated system. So I'm going to take my quantum system, look at the classical limit, and see if this gives you the behavior that we've already derived in the previous part of the course. So in order to do that, we're going to then be turning these sums over K. We're going to specify these states by momentum eigenstates. And so we're going to be having to sum over wave vectors K or momenta P. And in fact, what we're going to do is, we could do it that way, but I'm going to do it slightly differently. What I'm going to do is I'm going to actually do these sums. I'm going to turn these sums into integrals, just like we did when we derived our formula for the entropy. But there, I took the sums over states and turned them into integrals over wave number K. This time I'm going to do it, I'm going to turn the sums over states K into an integral over the energy E, and I'm going to then derive for you the most important formula in all of solid state physics, which is the density of states in energy. It's the only thing that I remember about solid state physics pretty much. So we're going to turn these sums into integrals, but this time over energy and not wave number. So that's going to be the strategy. And so as part of that, I want to remind you, or tell you for the first time in some cases, about the density of states in energy. So let me first of all write down for you what the result is, and then I'm going to derive it. So my claim is that I can convert any expectation value. So my claim is, if I take any quantity x, whatever it is, the expectation value of that is then going to be the sum over states, the occupation of those states, times the value of this quantity in the state K. And I claim that this thing is equal to, and hopefully I'm going to write it down correctly. It's not guaranteed that I will. 2m over h bar squared to the 3/2, and then the integral naught to infinity, x now as a function of energy, and then d density of states as a function of energy, d energy, like that. And my claim is that this formula d of a is v. Oh no. I told you I got it wrong. Let me write it like this. Like this. My claim is that this is v over 2 I squared 2m over h bar squared to the 3/2 epsilon to the 1/2, at least in 3 dimensions. And And then because and then I need another factor in here. So I'm sorry about the typos. Times f of epsilon d epsilon. So what's happened in here is I have the x in terms of energy, which is this x here. I have the distribution function, the Fermi-Dirac distribution, which is here. And then the thing that converts the sum over k into an integral over energy is this factor here. And this thing is called the density of states in energy. And so here's the proof of that. So we're going to start off with our energy as a function of wave number. So energy is p squared over 2m, which in quantum mechanics is h bar squared k squared over 2m, where k is wave number. So then if I want to work out what is dk by d epsilon, that is 1 over d epsilon by dk. And that I can write as h bar squared over m, and then 2m epsilon over h bar squared to the 1/2, and all of that to the -1. So that's what dk by dx epsilon is. So then what that says is, if I write down the expectation value of some quantity x, so that is then the sum over states, f of k, x of k, and then that is going to be the following. Let me write it in wave number. So it's going to be v over 2 pi cubed. That was the density of states in k space. And then we're going to be integrating from k is going 0 to infinity. d3k is 4 pi k squared dk. And then the distribution function as a function of k, and then the quantity that I care about, x, as a function of k. So that is the result of just doing the sum over k space. And if I've got spin 1/2 fermions, I might have a factor of 2 in here. And this 2 is the spin degeneracy. Or S equals 1/2 fermions. So such as you would encounter for electrons in a solid. And so then when we do the calculation, just plugging it in, then we get that the expectation of x is equal to v over 2 pi squared 2m over h bar squared to the 3/2, the integral from 0 to infinity, x of epsilon, distribution function as a function of epsilon, and then epsilon to the 1/2, and then d epsilon. So that's the thing that we have to do, and that's called the density of states in energy, and that's how we use it. All right, so that's what the density of states is. Now I want to take the classical limit. So let's talk about the classical limit. So we will try to see if our quantum formula in the high temperature limit matches the Sackur-Tetrode formula that we derived before. That's our strategy. So what is going to be the classical limit? Jake, you have a question?
Could you explain again the difference between f sub k and f of e?
Yes. So f of k is the distribution function as a function of wave number of the state. And then if I know the wave number of the state, then I know the momentum of the state. If I know the momentum of the state, then I know the energy of the state, because the energy of the state is just p squared over 2m. So then I can ask, if I know the function is a function of momentum, then I can also say what the function is as a function of energy. And that's it. Okay, and when you know this Fermi-Dirac distribution, you know it. You learned it on your mother's knee, or you were taught it on your mother's knee as a distribution function in terms of energy. All right, so that's how we're going to do that calculation. So let's now talk about what is the basic point. So the basic point of the classical limit, and we will come back to this later when we revisit the Fermi-Dirac distribution function in more detail later in the class. But the basic point of the quantum limit is that only the lowest quantum states are occupied at very low temperatures. And in fact, later we will see that what we mean is that we're talking about temperatures below the Fermi degeneracy temperature, and which for many metals is say order 1,000 degrees or something like this. So then in the quantum limit, F is basically either 0 or 1, and virtually nothing in between. That's true, very close to absolute zero. In the classical limit, then what's happening is that the temperature is very high, and high energy states are occupied. And if high energy states are occupied, then that must mean that the occupation number of any given state is going to be very small. Okay, why is that? Well, because we know there's only a fixed number of particles in the system. So if at very low temperatures, all the states below a certain energy were all occupied, and then beyond that, virtually none were occupied, if I now increase the temperature and occupy all the high energy states, then the average occupation number of any state is going to be very small compared with one. So this is basically the picture, and we will derive this picture in more detail later. So if you haven't seen it before, don't panic. You will indeed, I will come back and explain it later when we derive this properly. For now, we're just deriving this as an epiphenomenon of the principle of detail balance, but we will derive it in detail later. So here is 1, here is 0, and at absolute 0, you would have this as your distribution function. You just put the particles into lowest line quantum states until you've used up all the quantum particles. This thing here is called the Fermi level, and we will explain it and calculate it much later. So that's at T equals 0. If I look at some temperature slightly higher than T greater than 0, but still less than the Fermi degeneracy temperature, this distribution will look like this. So this is what happens for T greater than 0, but much less than what's called the Fermi temperature. And then if I look at what happens classically, what's going to happen is that classically, here's F of E, here is the energy of the system. So these are the low-lying quantum states. These are the lowest energy quantum states. And all these high energy ones are empty when you're in the quantum limit, but the high energy states are occupied when you're at high temperatures. So if they're occupied, then what must happen is that now the tail of this distribution goes all the way up to here. And so because the total area under the curve has to be equal 1, then what that must mean is that this area here and this area here have to be equal areas. And so what that means is that in this limit, the occupation number of any given quantum state has to be much, much less than 1. So that is what is going to happen then in our classical limit. All right, so if f is much less than 1, then now let's go back to our formula for the distribution function. So our formula for the distribution function is the one that is starred at the bottom of the left-hand panel. That is 1 over 1 plus e to the alpha plus beta e. So when f is much less than 1, then our formula, our Fermi-Dirac distribution, becomes f of state k goes as e to the minus alpha minus beta e of k. So it goes like that. So the f function is much, much less than 1. If the f function is much less than 1, the only way that can happen is if the denominator is much larger than 1. If the denominator is much larger than 1, then the factor e to the alpha plus beta ei must be much larger than 1, and therefore then f has the form that I've shown over here. So if this is true, then that is why this would guarantee that f is much less than 1, because the denominator is very large, and therefore the e to the alpha plus beta e must be much larger than 1, and so we get that condition. Okay, so that's the simplification for this form. Okay, so now let me finish the calculation, and then I'll take Jake. Jake had another question. What's your other question? I can carry on, right? Thanks. So that's the case. So now f has a much simpler form, and then we can do a calculation. So suppose that I ask, I've got two conserved quantities that we're trying to handle here. I've got the quantity E and I've got the quantity N. So what I can do is I can take the ratio of them. I can take the ratio of those two quantities and find the energy per particle. And the reason I want to do that is the following. If I do that, remember that my sum over k has all of this terrible stuff, these factors of v and 2m over h bar squared to the 3/2, as you can see on the left-hand panel. All of those factors, when I take the ratio of E over N, all those factors cancel out. So if we look at the ratio of E over N, and I invite you to check this for yourself, then that has the following form. All the three factors cancel out, and it just looks like this. D epsilon times epsilon to the 1/2, and epsilon to the 1/2 comes from the density of states and energy. Then I have the energy itself, so that's my epsilon. And then I have my factor of Fk. I have E to the minus beta epsilon. And then in the denominator, I have the integral from 0 to infinity, epsilon to the 1/2, E to the minus beta epsilon, d epsilon. Okay, so let's have a quick look at that. So this epsilon to the 1/2 comes from the density of states. This epsilon to the 1/2, the same thing. This epsilon over here, why is that here? Well, that's here because I'm computing the expectation value of the energy. So that's the thing that goes in the integral. In the numerator, I don't have that because in the numerator, I'm just computing over here the sum over states, and so there's no variable that is in my integral, so I don't have that factor of epsilon. And then why do I have e to the minus beta epsilon? Why don't I have e to the minus alpha minus beta epsilon? That's a question for you. It cancels. That's right. That's the great thing. The alpha cancels because it's present in the numerator and the denominator. That's exactly right. So now all I have to do is that integral And if you do that integral, and there is a trick to doing that integral, which if you want to ask me, I can show you in the discussion session. So you can almost do, well, you pretty much, you can do this integral in your head. So what you get is this, do the integral. And then you get the energy per particle, E over N, is 3 over 2 beta, where beta is this coefficient that we're trying to find. Okay, but what did we calculate in the Sacca-Tetrode formula? In the Sacca-Tetrode formula, and let me just go back and just remind you that we actually did this. So I have to go back a long way. Sorry about that. Probably there's a better way to do this, but what can you do? Here it is. Yeah, here it is. Over here in my recap from the previous lecture, look on the left-hand panel. Look over here. So remember, I derived this formula up here at the top of the screen on the left. That was the Sacca-Tetrode formula for the entropy of an ideal quantum gas in the classical limit. It's got its Planck constant in there to real quantum calculation. And when I compute the energy per particle by differentiating, by using the fact that the temperature inverse is defined as ds by dE, what did I get? I got that E was equal to 3/2 nkBT. So E over N is 3/2 KT. So this is then equal to 3 over 2 times KBT. And so that means that the coefficient beta is in fact 1 over KBT. So that coefficient that we have in our Fermi-Dirac distribution is 1 over KT. Okay. All right. I had, so Jake had a hand up and Andrew had a hand up. So do you guys want to ask your questions? No? Andrew, no? Jake?
Yes, sorry,
Be quick.
okay. I guess I'm confused why F is still between 0 and 1. I thought you said it was like the total number of the particle and then we given. Oh, I guess. You can only have one maximum in each state.
Right. Okay. All right. So now we can do the following. So now I've calculated beta. So now I need to calculate alpha. So let me tell you what the result is for alpha, and then I'm going to show you how I did the calculation. So the next thing we're going to do is determine alpha. And I'm going to tell you the result first, and then I'm going to derive it for you. So the result is this, that alpha is equal to minus the chemical potential over KT. So that's the result. Okay, so here's two things I want you to know. First thing is, we're going to derive that. And you'll just see there's the derivation and some algebra, and they'll be fine and you'll be done. However, you will still not understand what the chemical potential is. I polled the class before, and you all told me that you had no idea what chemical potential means or why we had to use it, and that's true because you haven't been taught it. And I will teach you that, but not today. So you're going to see that this thing is in fact the chemical potential, and you're going to see with your own eyes that that's what it is, but you're not going to understand it today. So chemical potential will remain for at least a week or so, a quantity that is mysterious to you, and you won't know why anybody cares about it, but eventually you will learn about it. And when you learn about that, it will be an epiphany, and it will change your life, and it'll be one of the most important things that you've ever seen, like listening to Beethoven's Seventh Symphony for the first time or something like that. Okay, it'll be an epiphany, but that you won't have that epiphany today. Okay, so now let me do for you the calculation. So here's the derivation. Here's the calculation. So what I'm going to do is I'm going to I'm going to use the constraint equation. I'm calling it the constraint equation because that's what I will call it in the rest of this class, that if I sum over the occupancies of all of the different quantum states, then that is equal to n. And we know that that our f of any quantum state is in this limit e to the minus alpha minus beta epsilon I. So that's the classical limit. We already know that beta is not just some random thing, it's actually 1 over kt. And so if I now do the calculation, n is equal to the sum over states fi, and then do the integral. And I'm just going to tell you what the result is. I'm not going to do all of it. What you will find is that n over v is equal to e to the minus alpha times 2 pi m kbt to the 3/2 over Planck's constant cubed. Okay, and what I did was I literally did the integral. I literally did the integral for n as an integral over states using my density of states and energy. So that's the integral, and you should all check that, and that would be a really good thing to do in the discussion section. Or just when you're on the bus coming into the university, whatever you want. Okay, so now I'm going to show you that this is equivalent. So now we will connect this to the Sacca-Tetrode formula. Now, how will I do that? Well, let's remind ourselves that the only thing we know about the chemical potential is that we get it from the entropy. So why do we want to do that? Yeah, good question. Why? And the answer is because we know that minus mu over T is equal to ds by dn at fixed E. So we know that from thermodynamics. And the Sacca-Tetrode formula tells us what S is. So here's a Sacca-Tetrode formula. S is equal to Kb n, and then it's log of V over n plus 3/2 log 4 pi m E over 3n h squared plus 5/2. Do you remember when I derived this formula for you, and I said, that 5/2 there, don't laugh at that. That number is incredibly important, okay? You remember I said that, and I said it deliberately to be mysterious. So here's how you can see why it's important. So now let us compute ds by dn. Compute ds by dn at fixed energy. And you can see that n occurs two places. It occurs here and it occurs in here. So now let's do that differentiation. So that is equal to Kb into the log of V over n times 4 pi m E over 3n h squared to the power 3/2 plus 5/2. That's doing the differential, that's differentiating with respect to this n, and then I have to differentiate to the n's inside the logarithms, and if you do that, you get minus Kb times 5/2. Why do you get 5/2? Well, you get one factor of 1 from here, and you get one factor of 3 halves from here, and they add up to 5 halves. So when you do the calculation, you can see that that 5 halves cancels. And then what I end up with is that I get KB times the quantity alpha that I already calculated over here on the left-hand page. So now I know that that is true, and so therefore I get, rearranging it, that alpha is equal to minus mu over KBT. So this quantity alpha is related to another quantity, which is the chemical potential, which means nothing to you now, but will mean something to you in the near future. And so now we can put it all together. And what that says is then the summary of this section is that the probability of observing a fermion in the quantum state I is equal to e to the epsilon I minus mu over kBt plus 1 to the power minus 1. And that is the Fermi-Dirac distribution. Fermi-Dirac distribution, and I want to comment. If you look in any textbook, we derive this from the Gibbs distribution. We derive this from the grand canonical distribution. So comment is the usual derivation. From the Gibbs distribution, or the grand canonical distribution, which I'm going to be teaching you shortly. So that's the usual distribution, but we didn't need to know any of that stuff. We just did this from the basic fundamental principles of quantum mechanics. So that's the first thing. So that's the we can also derive it. I can also derive this from quantum mechanics, and by that I mean second quantization. And for those of you who want to do this, in the discussion session, I put on Teams a homework sheet, not a homework sheet, a sort of review sheet on how to do second quantization in quantum mechanics, starting from almost nothing, going all the way up to deriving in a super cool way Fermi-Dirac distribution, the Bose-Einstein distribution for fermions and bosons, just using annihilation and creation operators. It's a one-line derivation. It's absolutely beautiful. It doesn't require any of the sort of very subtle and fundamental thinking that we've done here. In other words, the message is this: you can solve everything in statistical mechanics by just using these very basic principles about what it means to be in equilibrium. And the problem is, the message is that using those principles is very hard. It relies all on these clever arguments that I've been showing you the last week or two. And what we want to do is we want to find methods to do these calculations in a much simpler way, a much more straightforward way. And that's what we're going to be focusing on in the next section. So in order to do that, we're going to have to think not about isolated systems. Isolated systems are called the microcanonical distribution. If you want, that's just the formula. S is KB log gamma. That's called the microcanonical distribution in some books or in the syllabus. We're now going to be having to transition to not looking at isolated systems, but looking at systems in contact with a heat reservoir. And then we're going to derive the Boltzmann distribution from that. And the point about the next section of this class is, when you derive that, the question that most students have is, well, they learn about the Boltzmann distribution and the idea of ensembles and blah, 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 and they can parrot all of that. Everything that I tell you or read out of a book, the students will know how to say that, but you won't have a clue what it actually means physically. You won't have a clue. In my view, it's very bad pedagogy to explain things this way. So I will explain it to you. Once we do that, I will explain to you what is the physical interpretation, the connection, the physical connection between what we've done up to now and what we're going to be doing in the next couple of weeks. So that's the segue into the next part of the course. So the next part of the course is whatever section number I said that it was going to be, and that is going to be systems in thermal contact. So what did I say it was called? Let me look at my printed notes. Section 2.4. So in the printed notes, section 2.4 is on systems in thermal contact. And what is our goal? What we're going to find several things. One is real systems are not isolated. That's the first thing. We're going to see that when we put systems in contact, we're going to see that entropy increases. Bless you. If they're not at the same temperature. Bless you. And that will lead us to the statistical formulation of what you learned as the second law of thermodynamics. And then the big payoff is that we're going to derive what's called the canonical distribution or Boltzmann distribution. And that will give us a simpler way to calculate thermal averages than for isolated systems. Okay, so let me, I need to switch to my other notes. And somebody had a question. Andrew had a question. Go ahead with your question, Andrew.
Yeah, a few minutes ago, you started the sector of Ted Road, you pointed out the constant 5 halves.
Mhm.
When you spoke to this, it was fairly profound.
There's nothing profound about it.
Because when you took the derivative of S with respect to N, it seemed to become more of just a convenient constant to simplify math.
It wasn't a convenient constant. I mean, everything that was calculated, and it wasn't like, well, I put that in because I know it's going to simplify things later. It was all direct calculation. You know, there was nothing up my sleeve. Okay, it was all so that cancellation had to happen, and the fact that the 5 halves was there in my original calculation, which was like, okay, well, there's a 5 halves there. Well, big deal. Who cares? Could have been 17 over 194, but it turned out to be 5 halves, and it turned out to be important for then interpreting the alpha in the Fermi-Dirac distribution.
So, like, what is the physically, what is it there representing? Does it have something to do with the degrees of freedom of the gas?
No, I don't think so. I don't know what it represents physically. It's just the next. I don't know. I don't have a deep enough understanding to know why I would have expected that to happen. Okay. All right. So let me go now to my notes, and I just want to just check here what I'm going to be teaching you to make sure I don't go up the imaginary axis any more than usual. Okay. Okay. All right. So let's do this. So the next thing we're going to do is we are going to ask the question, how do I count states? For two systems in contact. Okay. So the way I'm going to approach this is as follows. It's kind of a bit of a more principled way of doing it than what we already did when we derived the condition for thermal equilibrium, being that the temperature is the same. So we're going to consider two systems, and they're going to have energy E1 and N1, E2 and N2 in the obvious way. And before they're placed in contact, then the total number of combined states of the system, total number of states of the combined system is just the product. So it's gamma, and that's going to be gamma of gamma 1 of system 1 with energy E1 and N1, and then system 2 with energy E2 and N2. So that's the state of the system. Now what we're going to do is we're going to allow the systems to exchange energy but not particles. And whether you think that's something reasonable is a good question, because it always seemed to me that it's not reasonable. How are they exchanging energy when the only things that can have energy in the systems are the particles moving around with their kinetic energy? But put that question aside, we will come back to that question. So we're going to say now the total number of particles in systems 1 and 2, they're not exchanging particles, but they are allowed to exchange energy. So that means that the total energy, E is equal to E1 plus E2, is conserved. So here's my system 1. Here's my system 2. I open up this mysterious door between the systems, which allows energy to go back and forth. But I've also put a box around the whole system, and then this whole thing is an isolated system. And that is the picture. So now you can say, if I know the isolated system has energy E, how many different quantum states can it be in? And now we have a different answer than what we had before, because now there's many different configurations of the energy distributed between system 1 and system 2. It could be that system 1 has most of the energy and system 2 has hardly any. Or it could be that they have half the energy each, or maybe system 2 has a lot more energy and system 1 has got a lot less energy. So basically, the total number of ways I can distribute the energy between the two systems is I can do it like this. I can say system 1 has energy E1, system 2 has energy, therefore, E minus E1, so that the total adds up to the total energy. And then I can sum over all possible values of the energy of system 1, and that is the and that is the total number of ways of finding the overall system in the quantum state E. And then we ask, well, what is equilibrium? So what we found from the principle of maximum probability is that the equilibrium is special values. E1 is equal to, let's call it E1 star. E2 is equal to E2 star, which then must be E minus E1 star. And that maximizes the thing in the product there, gamma of E1, gamma 2 of E2. So that was the idea. And the reason for this is essentially you're summing over all possible energies E1, but the equilibrium state is going to be overwhelmingly more likely than all the others. So that sum is going to be dominated by the equilibrium term, and then all the other terms in that sum are going to be small contributions. So what that means is then that gamma of E is equal to I'm going to write it like this: gamma 1 of E10, gamma 2 of E20, and then plus, I'll say what those mean in a minute, and then sum over E1 is not equal to E10 of gamma of E1, gamma 2, sorry, gamma 1 of E1, gamma 2 of E minus E1. So all I've done is I've separated out the initial configuration of the system. So this was the initial configuration. Between system 1 and system 2. So that's the initial partitioning. Notice that the term then every term on the right-hand side is positive. And so that means then that a gamma of E is greater than gamma 1 of E10, gamma 2 of E20. And that is true, but it could be also equal to it, because if I put the system in the initial state, I'd already set it to be in thermal equilibrium, then actually that thermal equilibrium state would be the one that is dominating the sum, and so then gamma of E would be equal to that. And so I have that this is equal, with the equality being if the initial condition is the equilibrium state. Equal if E10 is equal to E1 star, etc. So that inequality must be true. And now all I have to do is take the logarithm, take the logs, and that tells me that the entropy of the system with energy E is greater than or equal to the energy of the system initially like so, and that is the entropy of the combined system is greater than the total initial entropy. So what we've learned from this is that the entropy of the joint of the combined system has increased from the initial entropy. Okay, so that's the statistical version of the second law of thermodynamics. Andrew, you have a question?
Yeah, where you have the, gamma v is equal to gamma one e one. Equals zero, yes. Zero plus, yeah, that's summation. What is that second term inside the summation? Making sum two?
So that's gamma two. Gamma two of E minus E
Oh,
one.
well, okay, all right.
Okay. Sorry about the bad handwriting. Okay, question at the back. Yes. Can you remind me your name, please?
Gabriel?
Gabriel, yes.
So, when you have the equality, does that mean that then the second term, or the summation term, that goes to zero, or how do you?
Yes, it basically goes to zero or is much smaller than the first term.
Okay.
Okay, and I haven't really told you exactly how much smaller and so on. Okay, I don't want to fixate on that because I got much bigger fish to fry. Okay, Andrew,
Thanks. So that summation you have, are you assuming that those multiplicities, they're all much smaller than the multiplicity of the initial state?
no. This equation here, the one I just pointed out, that equation is exact. I've made no approximation, right? I've just taken out of the sum over E1 the term, which is the E1, which was the initial condition. Okay, so that's an exact equation, no approximation. Okay, all right. So let me just add one more thing. So well, we talked about, yeah. I'll just repeat myself from what I've done before. So the next question is, which way does energy flow? We talked about this before, but I'll say it again. So let's suppose that delta E is transferred, bless you, from system 1 to system 2. So then delta E1 is equal to minus delta E. And similarly, delta E2 is equal to plus delta E. So the total change in the entropy in doing that is then ds1 by dE1 times minus delta E plus ds2 by dE2 times plus delta E. So plus delta E because energy has gone into system 2, minus delta E because energy is taken out of system 1. And then by what we said before, this is minus 1 over T1 delta E plus 1 over T2 delta E, which is delta E times 1 over T2 minus 1 over T1. And so if if T1 is greater than T2, then that means that delta S is greater than 0. So the entropy of a combined system increases when the energy is transferred from a hot body to a cold body. So in words, entropy of a combined system is increased when energy is transferred from a hotter body to a colder body. And that's how thermodynamics was one of the axioms of thermodynamics. Okay, so now I want to talk about heat capacity. So you can ask the following question. Okay, how much energy must you transfer to a system to raise its temperature by an amount delta T? To raise the temperature of a system by an amount delta T. That's a question. So call the answer delta E. Then we define the heat capacity I'm going to call it C sub X is equal to dE by dt at constant X. So an X could be at constant volume or pressure or number of particles, whatever, constant magnetic field, whatever it might be. And we know that E is proportional to the size of the system. E is an extensive variable. And so therefore, then the heat capacity, that means that Cx is extensive as well, but it must reflect what the system is made of. So if I've got a system with a lot of particles in it, they can carry a lot of energy, so there may be a certain type of heat capacity, but what I really want to know is what is the heat capacity per particle, or what is the property of the physical system that doesn't depend on how big it is. So what we actually want to, what we would like a measure of heat capacity that is independent of the size of the system. And if it's independent of the size of the system, then what that means is it's therefore intrinsic to the system, therefore an intrinsic material property. So how do we get that? Well, a physicist would just say, well, I take the heat capacity and divide by n. So you might say little c of x is equal to big X, c of x divided by n. That would be the physics answer. But unfortunately, the first people who thought about this question and were interested in the answer were not physicists. They were chemists, and they had a different answer. So the conventional answer is Cx is equal to the total Cx, is the total heat capacity, divided by the mass of the system, not the number of atoms in it. So you have to take the number of atoms and then you have to multiply by, I don't know, the mass of the hydrogen atom, the mass of the proton in order to get it. So it's mass, not number, okay? And again, I didn't invent this, but that's the definition. That's the convention. I put a little sad face there. We just have to live with it. No point in griping about it. people, so as an example, this is called the specific heat. That's what this thing is. And for example, if I had copper, then this is 0.389 joules per Kelvin per gram. And it's that per gram that is the part that makes a physicist wince, but that's just the way it is. And this is done at presumably constant pressure. I think. Okay, so the next thing I want to do is I want to derive section 2.4.4. We're going to derive the Boltzmann distribution. And I'm not going to do it in the most mathematically sophisticated way that could be done using various mathematical tricks and so on. I want to explain it to you physically, so we're going to explain it in a very simple way, and I'm not going to start it today, and then we'll introduce the topic of the partition function. And a slick way to compute thermal averages. So that's going to be what we're going to do immediately on Wednesday. And I think I'm going to stop there. And I'll be happy to take any questions. So let me just turn off the Zoom, and then I can take questions. And then later,